So, good morning, everyone. Hope you're doing well. I hope you read the weather forecast, because otherwise you wouldn't know there's going to be rain today after yesterday, right? Surprising. Yesterday was a beautiful day. Last week, so far, I spoke about two kinds of potential. I spoke about v of x is equal to 0, and about v of x is equal to infinity or 0 when x is between 0 and L, and else it is infinity. Right? This is what we spoke about. And here, we said that psi is going to be ae to the ikx plus be to the minus ikx. And here, I said that the psi is going to be a sine kx plus b cosine kx, but here the cosines are 0. So this is what we saw so far, right? Now, of course, sines is two exponents, right? It's the same thing. This is the general convenient representation of the wave function for a free particle, where this one is a particle going to the right, and this one is a particle going to the left. Okay? It's a wave. Here, it was more convenient to speak about sines, because it was
stationary wave.
Because we had we knew that here psi must be 0, here psi must be 0, and because psi is continuous, continuous. Hope I wrote it right. And in case I didn't, you can just like go like this, and then no one knows what you meant. So because psi is continuous, we wanted psi of 0 to be 0 and psi of L to be L, and that's why we got only sines. This is a convenient representation here.
It's like a stationary wave. Stationary.
We said it is a stationary phase because, like, every energy has a different psi. This here killed the cosine, and the other boundary condition gave us quantization, giving me specific energies that are allowed, specific psi's that are allowed, which were just all sines. Okay? Now, today we're going to talk about v of x. It looks like, I'm not there yet.
So, it's like a lot of things.
Yes, it is a lot of things. And we'll talk about psi looking at stuff like this. It can be like this. It can be like this. It can be like this. Stuff like that. Okay? And here, we're going to choose to talk about this representation of a free particle, because the energy is going to be higher than this. This is going to be the energy. Okay? Maybe I should write letters here. This is going to be the energy. And this is going to be V. Okay? So, and here I'm a free particle, and here I'm a free particle, right? But this K here had to do with the energy, with my kinetic energy. And the energy here is different than the energy here. So how do we deal with this? What we're going to ask for is a few conditions. I'm just giving you the general algorithm. I'm spending about 10 minutes telling you what we're dealing with, and then we'll actually start solving a problem. Okay? What we're going to want is for psi to be continuous, and for psi prime to be continuous. This is going to be the two requirements. What are we going to ask? What we're usually going to ask is what are R and t. Did you say this in the lecture already?
No.
Okay. We saw r and t in
Waves.
in waves. Possibly. Did anyone here learn optics other than Joseph?
No.
So in optics, we could talk about a wave going to I don't know, a glass, and what goes back, what is reflected, and what is transmitted. Wait a second. Reflected, transmitted. This is R and T. R is reflected wave. And T is transmitted. This is what we're going to ask. What are R and what is T? What we're going to have is a wave. And if this is the energy, I'm going to say this is my wave. And when it gets here, it splits into two. One wave is transmitted, and the other part is reflected. And this is going to give me the condition on what happens here. And in order to understand all this, I need to introduce another quantity. Why is it not going there? Now it is not. Aha! I'm going to discuss J. J is going to be H bar over M, the imaginary part of psi complex conjugate psi prime. This is going to be J. J is going to be the current, the probability current. I will explain to you briefly what it means, and you're not fully going to understand me. You will fully understand this in the lecture. I'm going to tell you basically what it is, but you will understand, hopefully, how to work with it. The scenario I described here is not kosher, not possible in quantum mechanics. Because I just spoke about a particle coming here with a specific K, with a specific energy. If I know the energy, I know the K. And splitting into two. But if I know the energy and I know the momentum, what can I not know?
The position.
The position. So how can I know that it's coming from the left? Impossible. We're going to talk about something else, which is the probability to find the particle anywhere, but the current of that. This is the definition of this current. So I'm going to have here the current coming in, J in. Here I'm going to have the current transmitted. And here I'm going to have the current reflected. And I am telling you that R is going to be J reflected over J in, and T is going to be J transmitted over J in. I think I'm supposed to put I'm supposed to put this here. And of course R plus T is going to equal 1. Because the initial current splits into two.
I work with the current because of the fact that I can't know the P and X both.
Yes. Now I want to talk a little bit more about the relationship between classical physics and quantum physics. what we have here is a particle that has enough energy to go on top of this potential barrier. Classically speaking, it should just go through, right? What do I expect? I expect, now, in quantum mechanics, there is a certain probability of yet being reflected by this. I expect that if V naught is going to be 0, meaning it's basically no blockage, no potential barrier, I expect R to be R, the reflected wave, to be 0. If V naught is going to be infinity, it's a very, very big barrier, then I expect R to be 1 and T to be 0. When my energy is infinity, whatever. When my energy is infinity, I don't even notice this potential barrier, right? So I expect R to be
0.
Okay, now this is true here. The same thing should happen here, right? Here, again, the same thing. I'm going to have, this is completely counterintuitive. Here I have a certain energy, a certain kinetic energy. And here, my kinetic energy is increasing. I expect to only go faster. We can even talk, you know what, we're going to talk about this for a second. I expect to go faster now, yet there is a probability of being reflected by this step. So I'm going to have R, and again I get out what happens at different extremes to see that my answer goes back to classical physics. Okay, this is what we're going to do today.
V0 is the step. Right?
Yeah, V0 is the step. One last thing that we're going to do at the end is something that's not physical, not possible, yet part of this course in every university, which is, so you were all wondering why did I do this last one, right? Aha, I did it on purpose. Because we're going to do here a delta barrier. We don't have delta, it doesn't exist, something that diverges to infinity with the width of 0. Yet, it is one of the a blockage that people like to talk about, so we're going to do this here, and you're going to also have it to the homework. What we're going to do today is we're going to solve one of these problems, I don't remember which one, to the end. And the rest, I'll do the important parts. Okay? Any questions so far? Okay. These are my guidelines. This is my J. Psi is continuous, psi prime is continuous. The questions are, what are R and T? When R and T are these, and when J is this. Oh, there's one last thing that I didn't mention. What did I want to say? Oh, yes. How do I define R and T? Oh, maybe I'll talk about it later. Yeah, I'll talk about it now. How do I define R and T here? Here I have only two areas of the potential, right? Here it's 0 and here it's minus V naught. V naught is the VFS.
Thanks for the translation.
For the clarification. What happens when I have a wave coming here?
The first split.
It splits twice, right? I'm going to have here whatever comes in. Here it splits to this and this. Now here it's split again, right?
Yes.
To this and to this.
But he's
and here it's split again, right? But I can say at the end of the day I have here 5 waves.
But the one
I'm going to talk about this one as JT and this one as JR.
The one that's come left from the last split, going to split again.
Yes, but at the end of the day,
He will be 0. Yes.
Some particles will join JR, and another will join this. It will join back this and this and this. There's like an infinite circle here, right?
Yes.
But at the end of the day, I can ask, what is the J going left here? What is the J going right here? What is the J going left here? the point at the end is, I just wanted to mention that when I ask what is R, what is T, what is transmitted, when I ask what is transmitted, I'm not talking about this. I'm talking about this. When I ask what is reflected, I'm not talking about this. I'm asking about this. This is just the language used here. This was a long introduction. It's just a little frustrating because we didn't dirty our hands, besides me. Let's do some physics. This is way better than the thing before. Okay, I'm here at page 5 of the document here in the wheel. Thank you to whoever erased the whiteboard. Who was it? You. What's your name again?
Ravid.
Ravid? What does it mean?
תכשיט.
Ravid הזהב על צווארו. Correct. Joseph had one. Joseph, you had a Ravid. In the Bible. Oh, really? Anyway, this is random. We have here a potential barrier. This is one of the scenarios I described before. We have a particle, a free particle, energy E, momentum H bar K, released from X is minus infinity towards X goes to plus infinity and meets meet with an A, right? The potential barrier V of X is equal to V naught when X is positive and 0 when X is negative. Find T and R when E is bigger than V naught. If I want it right, I have this. So, what I have here is here I write with psi left. It is AE to the IKX plus BE to the minus IKX. Can someone remind me what K is?
Momentum.
It's the momentum and it's
divided by H bar.
the momentum divided by H bar, and what's the relationship to the energy? If I want to do that, I can rewrite the Schrödinger equation on the left hand side. I'm going to write the left hand the Schrödinger equation on the left hand side. The left hand side V is 0. I have minus H bar squared psi double prime over 2m plus 0 times psi is equal to E psi, right? So psi double prime is equal to minus 2me over square root of 2me over H bar psi. No. No, ממש לא. Yeah, like this. Yeah. Good. And this is k squared. So k is equal to the square root of 2me over h bar squared, or square root of 2me over h bar. So this is the k I have here. I know that the particle is coming from infinity, so psi in is just this. This is psi in, right? Now what is psi right? Here I have the particle splits in half, right? This is what goes in, and it splits in half to this guy and this guy. This guy, I can say this is the coming wave. This is the reflected wave going to the left. This one has a positive k, this has minus k because it goes to the left. And this one goes to the front. Psi right, if I were to write this Schrödinger equation, only write V naught here, what would I get? Minus h by squared over 2m psi double prime plus V naught psi is equal to E psi. Here I'm solving the Schrödinger equation on the left side. It's a little confusing because it's on the right side, but it's on my left. And on the right side, I have this. I can move the V naught to the other side. Minus h bar squared over 2m psi double prime is equal to E minus V naught times psi. This is very similar to this. This time, my k is going to be square root of 2m E minus V naught over h bar. Now I want to use the letters like k. So I'm going to call this thing k and this thing q. And the solution of psi right is going to be c e to the I qx plus dE to the minus I qx. Right? I have here two exponents. I have here, I don't know, harmonic oscillator. I could write it as a sine, as a cosine. I choose to write it as exponents going right or left. Here I have an exponent going right, an exponent going left, but here I only have a guy going to the right. So this one is 0. This is the first step. The first step in these problems, I didn't use the word scattering yet. This is the word for this. This is the title for today's lesson and for today's homework. Scattering in Hebrew? Very good, very good. Scattering in Chinese? Scattering in Spanish?
Dispersión.
Okay. That sounds about right. Okay, so after we write psi in every region separately, we want to make sure these two things are kept. Okay, I have here 1, 2, 3 constants. I have here 2 equations. I'm gonna be stuck with one constant, right? Let's see what happens to it. I want psi at 0 minus to equal psi at 0 plus. This gives me A plus B is equal to C. I also want psi prime of 0 minus to equal psi prime of 0 plus. This will give me IK times A minus B is equal to IQ times C. You all see it? Are there any questions? This thing is the same thing in every single of these problems.
Why the first equation is making sense, but the Q and K is different things?
I solved here the Schrödinger equation on the left side and the Schrödinger equation on the right side. And got here a K and here a Q.
Yeah.
This is okay?
The psi 0 minus. Yeah.
When I put instead of x, I put 0. I got here a plus b. I should have said it. You're right. I felt like I'm skipping something. I didn't know what. When I put here a 0, I should explain how I got this. When I put a 0 here, I got a plus b.
Yeah.
When I put a 0 here, I get c. A plus b is equal to c. Here, I first do the derivative, and only then I plug in 0. When I do the derivative here, it just multiplies everything by ik. And here, it multiplies everything by minus ik. So here I get ik times a minus b. And here I get iq times c. Okay, this is nice. I got here 2 equations with 3 unknowns. Pretty annoying, right? This is the point in which I leave this. I'm going to write it here separately. A plus b is equal to c. And iq a minus b is equal to iqc. And then I'm remembering that what I'm interested in is jr divided by jn and jt divided by jn. What does that mean? Let's see. What is jn? The coming wave is e to the ikx, right?
Why do you get e to the ik?
This is what's coming, right?
Yes, but you give the formula h bar divided by m.
No, sorry, yeah, exactly. The psi I want to plug in here
Yes.
is going to be, so here, we're going to have here h bar divided by m, the imaginary part of psi complex conjugate is going to be e to the ikx complex times psi prime. So I'm going to have ae to the ikx prime. I'm trying to do it slowly. So this is the prime, and you have to take the complex conjugate. So I'm going to have h bar divided by m, the imaginary part of, here I'm going to have a squared, because I have a times a. E to the ikx and e to the minus ik is going to give me 0. Times ik. Is going to give me 1 times ik. Hey, the imaginary part only means to take the I out.
K squared.
So I get here h bar over m
K
a squared k. What is going to be j reflected?
J
Is it the same?
With B.
What?
It's kind of the same, but with B. Right?
Kind of the same, but with b. With a minus or with a plus? I'm always confused with this. But it doesn't
the
really.
exponent has minus, but
It
plus.
doesn't really matter because I'm gonna put the absolute value on it. And it's gonna be plus minus. Wait a second. I'm gonna have a minus. So JR is going to be minus h bar b squared k divided by m. What will be JT? It's going to be just like this, only with a C and with a Q. JT is going to be h bar C squared Q divided by M. Now I'm remembering that what I'm interested in is R and T. JR divided by JN and JT divided by JN. May I erase all this? Going once, going twice, yay. Now I know that my R is going to be, what I'm interested at the end, R is going to be JR divided by JN, right? With an absolute value. If I divide this by that, what do I get?
The amplitude squared divided by the amplitude squared.
B over A squared, right? The amplitude squared over the amplitude squared. And T is going to be
C over A with an absolute value.
wrong.
Oh,
K divided
Aha.
by C also.
C over A. Put it like this. Times C over K or K over C?
Q over
Q
K.
over K.
Q over K. Good. Now, these two things are the things, when I come to talking about scattering, this is the thing that students get most confused about. 20 minutes ago, I told you about an equation. J is this. It's very easy to forget about this because most of the work is usually around this. Psi is continuous, psi prime is continuous. What are the boundary conditions? Where did we start? Where there's a plus? Where there's a minus? Let's do the derivative. All those things. And then I get to this, and I might think I'm finished. And I can just do R as B divided by A and T as C divided by A squared.
You need to connect them.
But
This.
people often forget this Q over K. Because this Q over K goes back to the current, and the current is a new term that you forgot about, and this is the only context in which you use it. Problems of scattering. It's very, very easy to forget it, and just think that T is C over A, as Eliyahu said. Eliyahu, you did that mistake purposely so I can talk about it, so I appreciate it. Thank you. So I have these two equations, and now I'm realizing I do not need to know what is A. All I'm interested in, B over A. I can A plus B is equal to C, right? May I divide everything by A? 1 plus B over A is equal to C over A. I have this thing. Let's divide it also by A. I have IK times 1 minus B over A is equal to IQ C over A. This makes me very happy. Here I have only two equations with two unknowns. Now I'm good, right? I will not know what A is, but it doesn't matter. What I'm interested in is B over A and C over A.
You can divide it by I, this equation.
Yes, will it make you happy?
Very, very happy. Thank you very much. Wow.
My
Make my
pleasure.
day.
You weren't smiling like this before. You may be sarcastic, but you seem happy to me.
No, it's really, really exciting.
Good.
Thank you.
If you want to find A, you can do it from the normalization condition.
Yes, but we're never going to ask you that. It's always the same. What I just did now, dividing by A is always the same trick. I divide by A to get these two equations. Now I just need to F. So it says here. Makes me happy as well. Now, we plug in C over A from here to here. So I'm going to get K 1 minus B over A is equal to Q times 1 plus B over A. So I'm going to have here B over A times Q plus K is equal to, I moved everything that has to do with B over A to the right hand side, is equal to K
Plus Q.
minus Q. Because when I move this to the left side, I get this. Which is why B over A is equal to Q plus K, K plus Q, divided by K minus Q. Usually, this is B over A. What I'm interested in is R. So R will be this squared.
the over X or the opposite because it's K minus Q divided by Q plus.
Thank you, thank you. So here there is a plus and here there's a minus. Which comes to teach you that people should have less self-confidence and look more at the whiteboard. Now, I want to check the physics. I want to check that my energy is infinity, so maybe I'm not transmitted at all. Maybe R was going to be 1. I want to see that if V naught is 0, then I'm not reflected at all. Right? If this is my if the height of my step here is V naught, but it's 0, it should not be reflected. It should be only transmitted. Let's check it out. How do I check it out? I need to go back to terms that include the energy and V naught. So I'm remembering that K was the square root of 2me over h bar, and that Q was the square root of 2m e minus v naught over h bar. So now I need to do the square of this. I don't want to. I really don't. Okay. What I'm going to have here, k minus q, k plus q, they're all going to have the 2m over h bar. The square root of 2m over h bar can cancel out. They're both in the numerator and the denominator. So R is going to be...
I think it's going to be easier if you multiply both of them by k minus q. Then already the denominator is not
By k minus q?
Yeah.
Probably you're right. You want to do that? Okay.
Make it more complicated.
So I have here k minus q squared over k squared minus q squared.
All of that.
What?
All of that squared.
What?
It's k
It's all
plus
squared.
q squared.
K plus q. Then why would it be easier?
Because k and q have square roots, and if each one of them is going to be squared,
Yeah, but
you're
if
not
you...
going to have roots in the denominator.
I know, but you can't really get rid of it. Like the last term is going to include square roots anyway. You can't really get rid of it. Okay. The 2m over h, square root of 2m over h bar is going to stay there. What I'm left here is the square root of e minus the square root of e minus v naught divided by the same thing with a plus in between them. All this squared. Maybe you're right, I don't know. But here I have e plus e minus v naught minus 2 times the square root of this times that. Divided by the same thing, only with a plus. E plus e minus v naught plus 2m square root of e This is not nice. That's the
And
Of-
there isn't an m.
of course no m. What do you see in m? Of course, you can see that we have something dimensionless, which is what we expect. Is everything transmitted? It's 1 or 0, but not a mass or a velocity or something of any of this type.
And you can see that it's only 0 if it's only 1 if only be 0 with 0 in general. So
Yeah, I'm not there yet. I'm not as fast as you are. I'm going to divide everything by e. So I get here 2 minus V naught divided by E minus 2 square root of, and here 1 minus V naught over E. נכון? Yes, that is true. Divided by the same thing, only with a plus. Okay, this is R. When is R equal to 1? When is everything? Wait a second, let's see first what happens when E is way bigger than V naught. So all this thing here is 0.
This is also 0. It gets to 0.
No, 1.
1.
1.
2 minus
0.
2 plus 2.
It's 0.
0.
It's 0?
2 minus
2
2
minus 2 divided by
by 4. It's 0.
Because it's 2 minus 0 minus 2 times square.
Yes. Which makes me happy, right? I wanted R to be 0 and T to be 1. What happens? What is the next thing that I wanted to ask? What happens when
The other way.
V naught is 0? When V naught is 0, again I want. Oh, this is gonna be the same thing.
It's the same situation.
Yes. Okay. No, it's not the same situation. One is that there's no potential barrier at all, and one is that I'm at the classic limit. Therefore, I do not see this quantum barrier. And again, I'm that here R is equal to 0. What I would want to do also is check what happens when V naught is bigger than E. But I cannot do this. Why can I not do this? I cannot do this because
It was one of our assumptions, and it is in the square root, and you will have imaginary energy and.
exactly. One of my assumptions when I wrote Q, I wrote that psi double prime is equal to minus Q squared psi on the right hand side, where Q was a real number. This is my Q. If I have a potential barrier like this and my energy is here, so here I do not have oscillatory answers. What I have here is a decaying exponent. This is another solution. This is another scenario that we'll deal with very soon. So this is and the interesting part is exactly what happens when E is equal to V naught, and this is a very, very surprising result. What would happen classically? I don't know, because it's exactly like if you're epsilon less than that, so you're completely reflected, and epsilon more than that, you're completely transmitted, right? What I get here when E is equal to V0 is that I am completely reflected, if I remember correctly. Let's see it. I have here, this is 0.
This is 2 minus 1.
Yeah,
2
R is
minus
1, yes. R is 1. Which is very surprising. Well, why is it such a beautiful number? This is something that... This is one of the results here. This was the first problem we solved here, and it's going to be the only problem I solve from beginning to end. But the steps are always the same. You define psi here, you define psi there. Then you do j divided by j, or I can just do, if it's easier for me, what I can always do is to do r as a over b squared, and t is going to be c over a squared times q divided by k.
That's b over. It always be true? We can remember it? Or?
Yes, with adjustments, meaning you need to see exactly what is k and what is q every time.
Yes.
Meaning there can be another scenario in which this is the potential and the 0 is here, okay? So here you have plus V naught and you have minus V naught. And my energy is here. I could do different scenarios like this, but this general term where R is this, and T is that, will always be true. As long as my energies are, the energy is higher than any other potential. Very soon we'll deal with other scenarios in which my energy is lower. Have you ever heard of the term tunneling?
Yeah.
Tunneling?
Yes.
It's awful.
What? Here we're going to have tunneling. For example, you have this beautiful problem. It looks fun, right? Just think how long it would be to do here psi is equal to psi prime. The continuity of psi and the continuity of psi prime at 1, 2, 3, 4 different points. It's a lot of math, a lot of numbers. We're not going to do this, and we're not going to ask you to do this. But again, here we're going to have oscillatory answers. Here we're going to have, I'm pressing this as if you can see what I'm pressing. And here we're going to have real exponents, right? One decaying and one diverging. You're not going to have any diverging exponent, just a decaying one. Otherwise, it's not normalizable usually.
Why you assume that?
But we'll get there soon. We'll get there soon, and then I'm going to solve this. But this was the only time we're solving all the way to the end. Now we're going to solve many other potential. We're just going to start and do the basic equations.
No. Can't you just calculate in general if you have a variable with a finite length and a finite height? You can find the general formula for T and R, and then just substitute the different V's.
You're saying these two?
Yeah, not necessarily these, because that's for an infinite distance. But yeah, you could just calculate it once and then use the same result 4 times. I don't think you need to do...
Oh, you're talking about this thing?
Yeah, I don't think you need to use continuity 4 times as if you're starting from scratch.
Yeah, you're right. You're not going to have to start from scratch every time. You're definitely right. So what you're going to have in your homework is exactly these kind of potentials. You're going to have a step, you're going to have a small pit, a small potential well, and stuff like that. It is tiring to erase this whiteboard. Okay, please don't look. That's going to be might give you a headache.
This is completely analog to electromagnetic waves, right?
Yes. And just like what Joseph just said, I can have electromagnetic wave going through a material, going through something. Do you remember the Snell law from high school?
Mm-hmm.
Where the angle is different and stuff like that? So this. So you can have a different K, and when light propagates through air or propagates through a wall, it has a different K, it has a different energy, and then it changes. And then again, you want everything to be continuous.
But there you can allow K to be imaginary for methods. It's interesting.
Yes, I don't remember that though. Okay, so there's a small mistake here with this document because they forgot to wrote a minus here. But other than this, let's talk about a potential barrier. Okay? Where is it here? It's right here, V. Well, here. What we're going to do to solve now is this problem where V of x is going to be here a step of height V naught of length 0 to L. And I want to talk about 2 different scenarios. One in which the energy is higher and one in which the energy is lower. Which first, it doesn't really matter. But let's do the first case where A is positive, where the energy is high. Okay, so here I have I'm going to have psi left, psi middle, and psi right. At the left side, I'm going to have AE to the ikx plus BE to the minus ikx. This one going in is the A, and there's another one going back, which is the BE to the minus ikx. Here I'm going to have the one going through, which is CE to the iqx, and another one here being reflected, DE to the minus iqx. And here I'm going to have, I'm not going to write E because E it is taken. I'm going to have here FE to the ikx, yk because it's the same k as here, plus GE to the minus ikx, but the G is 0. Because I have no one coming back from here. Okay?
Why there is no coming back?
Because there's nothing reflecting this wave. This wave propagates here towards infinity. There's nothing bringing back.
When it goes from L
0 to L, it does have.
epsilon, and from L minus epsilon to L plus epsilon, he don't reflect it, nothing.
Yes, he's reflected. That's why I have this guy, the D.
The D. Oh.
Okay. So, psi left is this. Psi left, right here. Psi left at x equals 0 is going to be A plus B. Psi left prime at x equals 0 is going to be ik A minus B. Now I'm working on like a machine. I already understood the concept. I just need to plug in the equation, do the continuity, and that's it. Sine meter is going to be CE to the I QX plus CE to the minus I QX. Psi m of 0 is going to be C, this is the D, C plus D. Psi prime of m at x equals 0 is going to be IQ C minus D. This is going to be when I sew this to that. But I also want to compare this to this, right? So, psi m of L is going to be CE to the IQL plus DE to the minus IQL. You understand this?
You wrote A.
Thank you. Is it always the same guy correcting me? Is it always the same guy correcting me? Because I keep making mistakes. Now it's like you all together on this against me. Okay, psi prime here is going to be.
It's not person.
It is mutual. No, it's good you're correcting me. I'm kidding. IQ I'm going to have here CE to the IQL minus DE to the minus IQL. And here I'm going to have psi right. I already said that it is FE to the IKL, psi prime, sorry, AE to the IK. X,
It's K.
psi right. Yes, here it is K again.
Okay.
Psi right of x equal L is FE to the I KL. Psi right prime at x equal L is IK FE to the I KL. May I erase all of this? At the end, what am I interested in? I want to know what is reflected and what is transmitted. What I just erased now? What I'm interested in is R, which is B over A squared, and T, which is not C. Here I have something else. F over A squared. Do I have to multiply by anything?
Q over K.
Yeah, but I want the momentum here divided by the momentum here, but the momentum in both of them are the same. Here I have K and here I have K. Do you understand this? Beforehand we had here Q over K. Why? Because I had a potential barrier going like this.
Right.
And here I had K, and here I had Q. But now I'm asking about what's happening here, and this and this both have K.
Before the step, the energy is the same as after the step.
Yes. Was this clear? So this is what I'm interested in, these two things. So let's count the equations we're going to have and the constants. We have 1, 2, 3, 4, 5 constants. We're going to have 4 equations. Psi is equal to psi, and psi prime is equal to psi prime. Psi is equal to psi, psi prime is equal to psi prime. We're going to have 5 unknown and 4 equations. But it's fine, because we're going to divide everything by A. Let's do this. We're not going to do this all the way. But we're just going to write the equations. Well, A plus B is equal to C plus D. Then I have IK A minus B is equal to IQ C minus D. Then I have, oh no, this is sad, CE to the IQL plus DE to the minus IQL is equal to FE to the IKL. Then that's the equation 1, equation 2, equation 3. Let me rewrite equation 3. May I multiply everything by e to the IKL? I'm going to have D is equal to e to the 2 IKL times F minus C. Right? Did I do it right? I think I did. Yes, I did. Right? I multiplied everything by e to the IKL. So dE to the minus IKL times dE to the plus IKL, I'm left with D.
But you have Q.
It's
You
Q.
have Q.
Oh, it's a Q. Then never mind. Well, this is how you make things nicer, if it works. Then I have 4. I want to compare this to this. It's very sad. So I want to make Ben happy, don't we all? So Q, no I's here,
Yes.
times CE to the IQL minus DE to the minus IQL is equal to K FE to the IKL. I divide everything by A, and so on and so forth until I get these two things. Is the algorithm clear enough? Was the subtle point of the fact that I'm not multiplying this by Q over K clear? It comes back from the current that I defined, that I did not really explain to you why it's the term, but that's where it comes from.
A question about G.
Yes.
You said G equals 0. So it makes sense, right? Is there a more formal way to get G equals 0? Like some boundary condition to show it? Some normalization?
Maybe, I don't know it. Hey. Here's showing it again, the same thing. And now, I want to talk about a whole other case. Okay? I want to talk about the case where the energy is lower than the boundary condition, than the potential. Now my potential is going to be, my potential barrier is going to be this, again from 0 to L. But now my wave is a little lower. This is K, this is E whatever, which is the square root of 2m. So K is again square root of 2me over h bar. But now when I get here, I do not have exponent מורכבים.
Complex
exponents. Come on, there's a nice way to say it. I don't have these the sine and cosines. I'm going to have something else. What I'm going to have is real exponents. Let's show you that this is indeed the solution. Let's write the Schrödinger equation. I have here minus h bar squared over 2m psi double prime plus e naught psi is equal to e psi. Let's move the v naught here. Minus.
You didn't say that if this is the situation, the wave is reflected.
No. Chas v'shalom. Don't speak like that. No. If it goes to infinity, then it is. But here, we'll see that the wave is decaying. Tunneling, yes. I have minus h bar squared over 2m. Psi double prime is equal to e minus v naught psi. This is not surprising. This is exactly how it was with q before, right? Only this time, this thing is negative. Right? So it cancels out this minus. I have here h bar squared over 2m psi double prime is equal to
lambda.
v naught minus e psi. This is positive. Do you know any function that you do the derivative twice, you get the same function times a certain constant? Yeah, I know.
What?
What?
Which one?
It would be ce to the qx plus de to the minus qx.
Wow.
Right?
Right.
Where q is square root of 2m v naught minus e over h bar. Beforehand we had e minus v naught. Now I have v naught minus e because I want this thing, the square root, to be positive. So now I'm going to do the thing that anyone that has a whiteboard or a tablet can very easily do. Let's take off the eyes.
Yay! So much fun, Emmanuel.
Yeah?
All of the eyes go. My dream. There's
You're
no
very
imaginary
dark.
number.
You're very dark. Oh, you're talking about the eyes. I'm sorry. I was making a pun. My puns are not very successful, but... So now I have a whole other thing. I expect in general, are my x here positive or negative? My x here are positive. I should never have a diverging exponent because of the potential. So Eliyahu is not going to like this. But I'm going to erase this one just like I did before, I think. Actually, I'm not sure I do. Wait a second. Let's see what happens here. Maybe I should look at the notes. Do I have here what happens? Case 2 when E is 0.
Like if it's independent of L, then it should be possible. Because otherwise you could make L
Yes.
as large as you want.
Exactly, yes. I should have here a C. Because I'm going to have a C because I have eyes. Now, am I pushing it? I am, right? Okay. So these are my solutions, and then I need to correct all the equations accordingly. And then again, R&T are going to be this thing. Okay? So what we saw here is a tunneling through a potential barrier, and yet you will have something transmitted. What will be the term? This can be interesting. I can do all this math. Again, I'm going to have to erase now all the eyes here. I'm going to erase here the eyes. Here I still have an eye. And here I will have an eye now. Then it just added an eye here. No free meals here.
What the shape?
right? Because now I can't cancel both sides. So I will have an I here. And then again, I need to do all this math. I have here 4 equations. It's not fun, but it's not the end of the world.
The equation 2, you have to...
Yes, also equation 2, I have to remove the I. And I think now it's good. So
Why
again,
the only case stays with the I? Because it starts the... Oh, I don't know.
okay, so now let's see what would happen in this disgusting potential story. Writing the equation is going to be very, very easy. It's very long, but it's very, very technical. What we have here, maybe I should draw it on the whiteboard.
Now it's a different case.
Yeah, now I'm talking about a different case. We did the case where the energy is higher or lower than the potential barrier. Now we have here a very disgusting potential that will lead to many equations. I'm going to have here, I have 1, 2, 3, 4, 5 different regions, which makes, for each of them I have 2 constants besides the last one. So I'm going to have here 10 unknowns. Therefore, I'm going to have 9 equations, right?
You remember that when you wanted to check if C was 0, right? If you take the limit that the
Yes,
constant should be 0.
Yes, if I take the limit. Another case that we can talk about is the case of a potential barrier when I come with the energy here. Okay? What will I have here? I'm going to have a wave going here, a wave going back, and here I'm going to have a wave decaying and a wave diverging. If this wave diverging now is going to be not normalizable, therefore it's going to be 0.
Yeah, but C is independent of L, right?
I don't remember.
But because if it is independent, then I
think C depends on L. What I see here, whatever, there's L in all these equations. Okay. Does anyone find this case interesting that I should talk about it? We understood the concept already. Again, I'm not going to ask you. This is just another way to make sure you understood how to write these equations. Maybe I'll just quickly read it from the document. Should I? Should I not? You seem very not interested. I just write here, okay? Besides the area V2, I'm going to have the complex exponents, right? So here for between x2 and x3, between x2 and x3, I'm going to have a plus. The mistake here, whatever. It's the opposite. Here I'm supposed to have without a minus, but here I'm going to, yeah, this is correct here. I'm going to have here A1 plus B1, A2 plus B2. The area 3 is going to have real exponents and not complex ones. A4 plus A5 plus B4. The last area has only a wave propagating forward. And then I need to sew everything. Okay? Clear? We're good? Okay. And from here we move to the last fun case of the delta barrier. This is something that is completely new, meaning it is not, there's a specific trick here that I did not teach today. What we do when we have a potential barrier at the shape of delta. As you remember, when I wrote this solution, whatever, the ae to the minus ikx plus b to the minus ikx, it came from the Schrödinger equation, the one with the cat. So now we're going to start again from the Schrödinger equation, and what we're going to have, if you want, you can just remember it this way. We're going to have that psi is continuous, and psi prime has a jump from integration on Schrödinger equation.
Can you explain a little bit more why psi tag has a job?
Yes, this is what I'm about to do. I have here this thing. I have here a potential like this. I have a wave coming here. I should have done other colors, right? I have 3 colors, I might as well use them. And they all work. And this is my potential. 0 here, infinity here, and 0 here. Then I have a nice and kind wave coming here with e to the ikx, or ae to the ikx. What happens here? Well, the chances of measuring here the particle are definitely 0. Also because it has a width of 0, and also because the potential here is infinity. However, there is a chance of penetrating through, of tunneling through. As we said before, when there is a blockade, you can still penetrate it as long as it's finite. So I'm going to have here a transmitted wave of CE to the ikx. K here and K here are the same. And I'm going to have here BE to the minus ikx. So how am I talking about? What effect does the delta have? So I'm telling you that psi is still going to be continuous, so a plus b is going to be 0. What will be psi prime? It is a little hard to discuss it because I don't know how delta behaves, right? What we're going to have here is v of x going to be at a certain constant beta times delta of x. What?
You say a plus b is going to be 0.
A plus b is going to be c, sorry. So this is my v. What I do now is that whenever I'm not sure, I just start with writing the Schrödinger equation. Minus h bar squared over 2m psi double prime plus, what is v of psi? V of x. It is beta delta of x times psi is equal to e psi. And what we're going to do to this equation is a very, very specific trick. There's no reason that you would think about it on your own. We're going to integrate both sides from minus epsilon to epsilon dx. Now let's see what happens. I have here minus h bar squared over 2m. When I integrate psi double prime, I get psi prime from minus epsilon to plus epsilon. Plus, what is this thing?
Beta psi of 0.
Beta psi of 0 is going to equal
E psi. No. E into psi.
e the integral of psi
dx
from minus epsilon to epsilon, right? But psi is continuous. Psi doesn't have crazy jumps. Psi is physical almost. Psi squared is physical, right? It's probability of finding the particle, whatever. I don't expect to have crazy jumps in psi. Therefore, this thing is going to be 0.
Since epsilons are really small.
Yes.
Can you explain why it's 0?
Yes. Now we're asking, this here is psi. It is the square root of rho. It is the probability of finding the particle between minus epsilon and plus epsilon. What is the probability to find a particle between here and here?
0.
What is the probability to find a particle between here and here? Or between here and here? This thing goes to 0. As the width goes to 0, I can take now a limit of epsilon goes to 0. Okay. So what I have here is minus h bar squared over 2m psi of epsilon plus h bar squared over 2m psi of minus epsilon is equal to minus beta psi of 0. Where? Here? Yes, thank you. No, this is not psi prime. I move this to the right side. I can do the minus and all this if I want. But from here I get the two equations. Now there's different manipulation that I can ask on this. I will soon say what they are. But what we got here is two very specific equations, just like we had before, that we can work with. And again, find what is C divided by A and B divided by A. From this point on, it is again very, very technical. What I'm going to have now is A plus B is C, therefore 1 plus B over C, B over A is C over A. This is going to be the first equation. The second equation is going to be psi prime of epsilon is ik A minus B. Minus, well, maybe I should keep the h bar over 2m. Let's do it this way. Psi prime of epsilon minus psi prime of minus epsilon equals 2m beta over h bar squared, psi of 0. Okay, let's get rid of all those constants in a more compact way. Psi prime of epsilon is ik A minus B. Sorry, this is psi k of epsilon is ikc, right? Plus epsilon is I have ikc. Minus psi prime of the left hand side is ik A minus B. This is 2m beta over h bar squared. Psi of 0 is going to be C. Divide everything by A and get ik C divided by A minus ik plus ik B divided by A is equal to 2m beta over h bar squared times C divided by A. So there's a very, very, very specific trick of finding what is the jump in the derivative of psi prime when you have there's a very specific trick of finding the jump in psi prime, the derivative of psi, when you have delta barrier. We got to this equation. Let's see what happens here. Is it identical? You have here ik times 1 plus b over a. That's what they have here. Is it the same thing? Ik c over a minus ik plus ik b over a is equal to 2m beta over a plus 1 c over a. Yes. So, what you can, if you follow here, you're going to get the results. T and R. Again, this document is in the Moodle. You can see that T plus R is 1. And here you have limiting cases of this thing. I don't find it too interesting. What can I ask about it? Well, in the homework, as far as I remember, we're going to look at it together in a second, but in the homework you have a delta pit, the exact opposite. What happens here again? What are R and T? There are different things that one can ask here. I can ask. One of the questions that that was in the exam a few years ago is this thing. You have a delta and this. So here you have a K and here you have a Q. That's it. What? You don't like it? Okay. Something else that once people did is talking about two deltas. Fun stuff. But what you get here is 2 more variables and 2 more equations. Not fun, but not the end of the world. Shall we look at the homework together?
למעלה.
No, I missed it. But
לא, אתה יכול ללחוץ על ההורדות.
PDF, כן.
So, here you're asked to show that this J thing works. Okay? That it works with the Schrodinger equation. Here you have a potential step. What happens in this limit? What happens in that limit? Again, we're doing exactly what we did in this exercise. E is bigger than V0 or E is smaller. Then you have a potential barrier of a specific length, which is exactly what we did again. Then you have the scattering by a potential well. This is something we did not do, but it is, again, the exact same math. You have a potential that goes like this. And my energy is here.
Oh, it's a well. It's a well.
Yes, it's a well.
No, it's a. You can,
Oh, it's finite?
Finite, yes.
Okay, so also something we didn't do. But it's very similar to what we did, right? Okay. And at the end you have a delta barrier. I thought it's a delta fit. Whatever. Okay. So enjoy. Good luck.
Thank you.
Maybe I'll add you another question of this delta. Alright? It's cute.
Very, very. יש שאלה משהו בבית.
כן.
אם יש לי איזשהו...
צריך לתפוס.
רבי, תשמור לי מקום.
אני רוצה לשאול דבר.
אם יש לי איזשהו...
זה ב-102.